Hello everyone again and welcome to this particular video, and in here we're going to be exploring applications of the magnetic force and uniform magnetic fields and current carrying conductors, and how this actually comes together in terms of considering not only the combination of components but also splitting a question into simple forms in order for you to tackle any form of electromagnetic problems in applied physics. So in here we're going to be introduced to the big idea question, where in here we are asked that a specific segment of conductor shown in the figure below, which is shown as the dark particular color, and we have various angles that actually are aligned in the y and the x components, and we see here that this actually dark specific image actually carries a current that is around 0.2 amperes, and the shorter segment, which is the one on the far left, is measured in length to be about 0.8 meters long, and the longer section, which is actually on the far right of that positive xy axis or quadrant, is actually 1.6 meters long. So the question asks you to determine the magnitude and the direction of the magnetic force on this specific conductor, and also given that the magnetic field is determined to be actually located on the x-axis, which is indicated by the unit vector I, and the magnitude is 1.9 teslas. So let's move on to how to solve problems involving physics by not only labeling the diagram but also being able to actually highlight some of the key components that the question actually presents to us. So in here we see that we have the unit vector, which is the I that is associated with the x-axis, and we have the unit vector, which is represented as j, to be laying on the y-axis. So the givens in this question implies that first we were given the current passing through this conductor to be 0.2 amperes, which we see right there. And the next thing here that we actually recognize is the length of the shortest wire, which is labeled as L1, and this is equal to 0.8 meters, and the associated angle to the x negative axis is actually alpha 1, which is equal to 45 degrees. And then the next thing that we are going to focus on is the other section of the wire, which is L2, and L2 is measured in length to be 1.6 meters, and this is also associated with the angle that is alpha 2, which is measured to be 30 degrees from the positive x-axis. So since we have these, we still have some other components left to go, which is recognizing the direction and the magnitude of the magnetic field, which is represented as B to be 1.9 teslas, and this is the information given in the question. This, you recognize the direction of the magnetic field to be in the direction exactly as positive I, which is the unit vector that is associated with the x-axis. So this question here requires us to determine the force, not only the magnitude but also the direction, and specifically looking at the magnetic force. So looking at the analysis, we see that for the analysis we need to not only do some combination but also splitting this particular conductor into two segments. So first here is to recognize that for a straight conductor, we actually determine the magnetic force from our previous videos on straight wires to be, in this case, equal to the multiplication of the current and the cross product of the length of the wire, which is in the same direction as the current, and that of the magnetic field. So once we're able to do that, we need to apply this skill and logic to the other segment of this particular analysis, which is combining the various components that are not only associated with the first length or the shortest length of that wire, which is going to be indicated as F1 for the force that is acting on that segment, and the other segment of the wire, which is F2, which is associated with L2. So the sum of these two components gives us the net force of the magnetic force. So in here, we're going to now deal with the analysis section of this particular exercise in here. And since we've highlighted the givens required and also looking at the analysis, we are going to actually apply this into this particular question, and we will go to first focus on F1, which is the force acting on, or the magnetic force acting on wire 1. So this, in this case, for we to analyze that, we're going to look at F1, and for F1 here, we're going to cut out the specific segment of that wire. So cutting that out, we actually recognize that there's an angle that will be associated to the positive region on the x-axis, and this angle corresponds in here to be 45 degrees for alpha 1 after you extend that length of the wire to the same direction all the way down, reaching the positive x-axis region. And the other thing to recognize is that the magnetic field is also on the x-axis in the same direction positively. So once you include that component in here, this will lead us to the direction of the magnetic force, and the direction of the magnetic force we recognize is the cross product of the length of the wire and that of the magnetic field. So we come to the conclusion that the force is actually parallel indeed to that of the K, which is a unit vector on the z-axis, which in this case is pointing towards us, because we see that the right hand rule that is applied to the combination of the length of the wire, 45 degrees to the magnetic field, results in the positive direction of the force magnetically in the positive K direction, which is pointing towards us. So therefore, to determine the magnitude of that particular force F1 on that line 1, we actually have to multiply the current to the cross product of that particular combination of the length of the wire and the magnetic field sine alpha 1. So therefore, once we have that established, we're going to do the same thing for force 2, which is associated with line 2. So in here we see that line 2, we actually cut out that specific other segment of the wire. We highlighted that in here we have the extended x-axis negatively to be determined in there, and then we have our magnetic field to be in the positive direction on the x-axis. And once you combine the same direction of that particular current in the counterclockwise direction, we actually come to the conclusion that our force is actually going to be produced in the negative direction, which is actually pointing away from this particular screen, which is associated with the negative K unit vector on the z axis. So therefore, in this case, once you do the counterclockwise from the current all the way to the magnetic field, we actually then result in a particular magnitude of that particular force on the second wire component to be the product of the current and the length of the wire 2 multiplied by the magnetic field sine 360 degrees minus the alpha 2. Now 360 degrees minus alpha 2 is exactly the same as negative of sine alpha 2. So therefore, in this case, we actually can determine the force on wire 2 to be equal to negative the current multiplied by the length of the wire 2 multiplied by the magnetic field sine alpha 2. So in this case, once we see that negative sign, we automatically know that the direction is actually on the negative z-axis, which is associated with negative k, the unit vector. So once we have these two information established, then we actually go into the solving section in here where we combine the two components to determine the magnetic force net. So therefore, since the net magnetic force is a combination of F2 magnitude and direction and that of the F1 magnitude and direction, we can then combine those two together in terms of the components, which is actually this expression. And then once you put in the direction, which in this case we will establish to be the k unit vector, we know that it is on the x-axis, but where specifically is it pointing? Is it pointing on the negative or on the positive direction? That will tell based on the established solution. So once we simplify the expression above, we actually have IB all multiplied by everything inside the bracket, which is the length of the wire times the sine of alpha 1 minus the length of the wire 2 times sine of alpha 2. And we still recognize that we don't know the direction yet when combining F1 and F2, so we're going to keep it as k unit vector, which is on the x-axis. So since we have the givens and we have the required, we're going to put all those variables information into the respective variables in that expression, and we're going to arrive at the solution, which is this, where 0.2 amperes was multiplied by 1.9 Tesla, and this result is multiplied by everything inside the bracket, which is line 1 length, which is 0.8 meters times sine of alpha 1, which is 45 degrees, minus inside the bracket 1.6 meters, which is line 2's length, multiplied by sine 30 degrees, which is alpha 2. And all this will be given into account when k is the direction. So where is the direction? The direction we notice is from the negative result of that expression, which is in this case negative 0.089 k, which is the unit vector on the x-axis, on the z-axis, newtons. And once we see that, we can actually come to the conclusion that the negative k is actually in the negative direction, which is pointing away from you, and the simplified or scientific notation of that particular value is going to be 89 millinewtons. So therefore, in conclusion, we have established the force not only in terms of the magnitude but also the direction. So therefore, in this case, the direction of the magnetic force net is actually pointing away from you, and this is actually associated with the z-axis, which is the unit vector k, and the magnitude in here is 89 millinewtons. So therefore, in conclusion, we're able to actually determine the magnitude and the direction of the magnetic force by first breaking the components first and then combining into one net magnetic force. Therefore, we're able to determine not only the magnitude but also the direction of that particular force. So that is about it for this particular video. These are the skills required enough for you to determine various magnetic forces involving various segments of straight wires. And please hit the comment down below, let me hear your thoughts about this, and please follow this particular video up by watching other videos that gives you the groundwork enough for you to solve these problems. And please don't forget to hit the like, share and subscribe. By that way I can talk to you all later. Stay smart and believe in yourselves.